For nearly 2 centuries, the Navier-Stokes equations have stood as one of the most formidable challenges in mathematics. These equations, which describe the motion of fluids, from water to air, underpin many scientific and engineering disciplines. Despite their significance, a complete solution has remained elusive, earning them a place among the 7 Millennium Prize Problems identified by the Clay Mathematics Institute, with a $1 million reward for a definitive solution. The difficulty lies in the chaotic and turbulent nature of fluid flow, where even minor changes can lead to unpredictable outcomes, a phenomenon evident in weather patterns, ocean currents, and aerodynamics. Professor Kamal Soltanov, a scientist and author of over 120 scientific papers, currently based in Turkey. Soltanov has made a bold claim. He has resolved a fundamental aspect of the Navier-Stokes problem. His research focuses on the uniqueness of weak solutions, addressing a question that has remained unanswered for nearly a century.
What is the next challenge for you? You have already achieved quite a lot, but the life is long and you have ambitions. What is the next challenge for you?
Before I began working on Navier-Stokes around 1985, I proved that when it comes to fixed-point theorems, these are usually proven using the Cassiopeia-Panache approach, which requires sufficient smoothness of the operator. At that time, when I was in Moscow at the Steklov Institute, there was a group working on the uniqueness of solutions to the Navier-Stokes equations. I've been working on this issue for over 40 years. I resolved this problem definitively in 2015.
Talking about the Navier-Stokes equations, in addition to being of great significance and interest in a purely mathematical sense, they're also very, very important from the engineering and medical point of views. They may be used to model the weather, ocean currents and water flow in a pipe, and also there's an application for the aircraft and cars, the study of blood flow. What are some other applications of your scientific activities which you think that benefit humanity at large?
Creating mathematical models is not easy. One must thoroughly understand the process, which often involves many components. It is essential to identify which components are significant and which are not. Unfortunately, this is not always possible. Nevertheless, mathematical models are necessary, or studying processes occurring in life.
He adds that the Navier-Stokes equations, a set of partial differential equations, describe the flow of incompressible viscous fluids in mathematical terms.
The Navier-Stokes equations, being a set of partial differential equations, describe the flow of incompressible viscous fluids in mathematical contours. Since the Navier-Stokes equation is non-linear, finding its solution had been impossible for years. 100 years after these equations were formulated, in 1932, the existence of a weak solution to the problem was proven, and the class of functions it belongs to was determined. However, the question of whether the solution is unique or not remained open. As a result, no progress had been made for 90 years. Though it may sound immodest, I have solved this problem. I do not hesitate to say that this is of great importance.
The implications of this breakthrough extend far beyond theoretical mathematics. The Navier-Stokes equations play a critical role in fields such as engineering, meteorology, medical science, and climate research. Soltanov's findings suggest that, under specific conditions, weak solutions, approximations that satisfy the equations in a less rigid sense, are indeed unique. If validated, this would represent a major step forward in mathematical physics and applied sciences. As the global scientific community scrutinizes his work, the world is left wondering, could this be the breakthrough that completely unlocks the Navier-Stokes equation? The question remains.